This presentation, which is part 4 of our series on distributions, discusses computing normal percentiles. As with the other presentations in this series, the instructional design for this presentation was developed by David Kleinbaum, statistician, and Anna Washington, educator. The narration was done by David Kleinbaum. We have already completed part 3, computing normal probabilities. Computing normal percentiles is similar. The same procedure is used in reverse. The goals of probability problems and percentile problems are contrasted here. In probability problems, you are given X and you seek the probability. In percentile problems, you are given the probability and you seek a value of X. The procedure is reversed. The procedures are contrasted here. Across the bottom, starting on the right, is the familiar Z-ifying procedure used to find probabilities. Given a value of X, Z-ify, then look up in the Z tables. Above, starting on the left, is the procedure for finding percentiles. Given a probability, look it up in the Z tables and then Xify to get a value of X. Let's see how this Xifying procedure works by getting back to weighing babies, a situation we discussed at length in part 3. The variable X that we consider is the birth weight of babies. The parameters are mean mu 3500 and standard deviation sigma 500. The parameters of the normal distribution may be written in brackets as shown above or drawn in the curve as shown below. Suppose for this normally distributed random variable birth weight, the health researcher asks, how much would a baby have to weigh to be heavier than most, say 95% of the babies in the community? The picture here is drawn to show that for this normal distribution of birth weights, we seek the point or value of X, to the left of which lies 95% of the area under the curve. We call this point the 95th percentile. This terminology may be somewhat confusing, so let's straighten things out. In this section, we seek a value of X called a percentile, or percent point, which describes a single point on the X-axis. This term percentile, corresponding to a value of X, is to be distinguished from the term percent. 95%, for example, refers to the 0.95 probability, which describes the area which is shaded. Thus, a percent describes an area under the distribution curve, whereas a percentile describes a point on the X-axis. It has become customary to denote the percentile of a variable like X by attaching a subscript to the variable which identifies the proportion specified. So for our birth weight variable X, the 95th percentile is denoted by X with subscript 0.95. Now, to get this percentile for X, we first find a percentile for Z. To do this, we consult the same Z tables that we use to find probabilities. Here's how to do it. In the Z table, read down the probability column instead of the Z column until you find the probability under consideration, in this case 0.95. Then go over to get the percentile of Z, in this case 1.645. This is the value of Z below which 95% of all Z values lie. Now that we have Z, the task becomes converting to X, or Xifying. And here is the Xifying conversion formula. To get X, use the formula inside the arrow. Take Z, multiply it by the standard deviation, and then add the mean. or x equal to mu plus sigma times z. This xifying formula shown on the left is just the opposite of the zifying formula for getting probabilities that you have already learned. Instead of subtracting mu from x and dividing by sigma to get z, you must add mu to sigma multiplied by z to get x. Thus, when you go in the opposite direction, you perform opposite operations. Here is the problem worked out using the xifying formula. The 95th percentile of x is given by 3500, which is mu, plus 500, which is sigma, multiplied by 1.645, which is z. The result obtained is 4,322.5. This means that 95% of the birth weights in the community are below 4,322.5 grams, which is the answer we seek. This cutoff point of 4,322.5 might be used by the health practitioner to classify future babies from this population as being of unusually high weight, an occurrence which might suggest a more detailed medical examination of the baby. Okay, so we can now identify the heavy babies, but what about the light ones, which might also be of interest? To identify both unusually light and unusually heavy babies at the same time requires us to consider 2 percentiles instead of 1. Suppose for our baby population we were interested in knowing the range of weights where most of the population was found, excluding babies that were either too heavy or too light. And supposed most babies means 95% of all birth weights. We then need to find two values of x which correspond to lower and upper percentiles of the normal distribution for the baby population. These points are labeled x sub L for lower and x sub U for upper. Because these 2 points, x sub L and x sub U, identify a middle area of 95% under the normal curve, we generally call these points the middle 95% points of the distribution. To find two such values of x, that is x sub L and x sub U, the procedure is the same as for a one-sided percentile, except that both sides must be treated now. First, we find the values of z by consulting the z table. And second, we xify both values using the conversion formula. Now we will solve the two-sided baby problem already mentioned. We first determine 2 percentiles of z by finding the two probabilities of z to look up in the z table. Since 95% is in the middle, 5% is left over for the tails, and we can use the property of symmetry to put 1/2 5% or 0.025 probability in each tail. Since the area to the left of the lower point is 0.025, this corresponds to the 2.5 percentile of z. To get the probability value of z for the upper percent point, add 0.025 to 0.95 and get 0.975, which corresponds to z sub 0.975. Looking up both of these probabilities in the z table, we get the 2 percentiles for z, minus 1.96 and 1.96. Incidentally, these two values are the negative of each other. In fact, because the z curve is centered at 0 and is symmetric, this is always the case. So the upper percentile of z is generally figured first, and then a minus sign attached to give the lower value. Now we must convert or xify both the values of z using the conversion formula on each one to give us the middle 95% points of x, which we have called x sub L and x sub U. Plugging in the mean 3500 and standard deviation 500, we come out with a lower percentile of 2520 and an upper percentile of 4480. The result is that 95% of birth weights in this community lie between 2,520 grams and 4,480 grams. Any weights outside these limits might then be considered either too light or too heavy. For a final example of computing percentiles or percent points, let's look at the variable blood pressure. This time we will call the variable y. Suppose we seek the middle 90% points of y. We assume that for the variable y, the mean is 140 and the standard deviation is 20. Remembering that only the upper point need be looked up, we note that for the 90th percentile, we actually have to look up the 90 plus 5 or 95% point of z in the z table. Going over to the z column in this table, we then get the percentile 1.645. So the upper percentile of z is 1.645 and the lower percentile is minus 1.645. Converting these values of z to y using the correct parameters mu equal to 140 and sigma equal to 20, we get a lower limit of 107.1 and an upper limit of 172.9. Thus, 90% of the blood pressures of this population are between 107.1 and 172.9. Persons with blood pressures outside these limits may possibly be considered for further clinical examinations. Here is a final problem for you to work upon completion of this presentation. Suppose maximum skull diameter for skulls from the pre-dynastic period follows the normal distribution with population mean of 133.58 and population standard deviation of 4.95. A new skull is dug up and measured to have a maximum diameter of 147. Does this fall within the middle 98% points of the distribution of pre-dynastic skulls? Here's a review of the procedure to use to answer this problem. Given a probability and parameters, use the z table to get z. Then xify to get x. This concludes part 4. We recommend working more problems using the viewing study guide provided with this presentation before proceeding to part 5, which concerns the normal approximation to binomial probabilities.